Right now, you're falling through a hole in space that's 2 billion light years wide. Back in 2013, scientists proved this was real, and most people still don't know about it. We're living inside something called the KBC void, a cosmic desert where there's 20% less matter than there should be. This empty space is twisting our view of reality itself. The universe seems to be expanding faster here than anywhere else, which breaks our most basic equations. We're going to explore the discovery that shook up cosmology, look at why 90% of space is empty, and understand what it means to be living in the cosmic outskirts. If you're ready to see the universe in a whole new way, hit that like button and subscribe to Mr. Sleepy Science. Get ready. Let's begin. 3 astronomers were counting galaxies when they spotted something that shouldn't exist. Ryan Keenan, Amy Barger, and Lennox Cowie looked at 35,000 galaxies in 2013, mapping where they were across billions of light years. The numbers didn't add up. Everywhere they looked near Earth, there were fewer galaxies than expected. Not just a little fewer, 20% fewer. This pattern stretched out in every direction for a billion light years, creating a sphere of cosmic emptiness with us close to the middle. This wasn't just a small gap between galaxy clusters. This was a void so big it shouldn't exist based on what we know about the universe. The researchers checked their data 3 times, used different galaxy surveys, and looked at the sky from multiple angles. The answer stayed the same. Our galaxy and everything around it sits inside a bubble of space, so huge it's bigger than anything we've ever seen before. The discovery got a name that sounds pretty casual: the KBC void, using the first letters of the 3 people who found it. But there's nothing casual about what this means. In the standard model of the universe, everything should be pretty even when you zoom out far enough. Sure, galaxies cluster together and leave empty spaces between them. That's normal. But a region this massive with this much missing matter pushes the limits of what random chance can explain. Computer simulations of how the universe grew from the Big Bang rarely make voids this large and this empty. When they do, it needs super rare starting conditions. The math says there's less than a 1 in 1,000 chance. Some scientists figured it would take a 10 sigma deviation from normal density. That means it's so unlikely you might not find one in the entire observable universe. Yet here we are, living in one. The implications started piling up right away. If we're in such an unusual spot, does that mess with every measurement we take? When we point our telescopes at distant supernova to see how fast the universe is expanding, are we seeing the true rate or a warped local version? The void idea offered an answer to one of the biggest mysteries in modern cosmology: the Hubble tension. For years, scientists have measured 2 different expansion rates, depending on whether they study the ancient universe or the nearby universe. The numbers disagree by 9%, which sounds small, but is actually a crisis. Both measurements are super precise. Both should match. They don't. If Earth sits inside a massive low-density region, gravity from the denser matter around the void would pull outward on galaxies inside it. That would add extra speed to their motion away from us, making the local expansion look faster than average. Suddenly, the conflicting measurements made sense. We're not measuring the universe wrong. We're measuring it from inside a hole. This changed everything, but it also raised an uncomfortable question that scientists are still wrestling with. If our location is this unusual, can we trust anything we think we know about space? What comes next shows just how weird our cosmic neighborhood really is. Cosmic voids aren't truly empty, which makes them even stranger than their name suggests. Between these lonely galaxies stretches space that mostly contains dark matter, dark energy, and occasional bits of hydrogen gas. The density is so low that gravity barely works. Without enough mass to pull things together, structure formation basically stops. No new galaxy clusters can form. No rich superclusters appear. The void stays a void. This emptiness has effects that ripple through physics itself. Gravity is already the weakest basic force in nature, needing huge masses like planets and stars to show real effects. In a void where mass is scarce, gravity becomes even less important. The main force becomes dark energy, the mysterious pressure that speeds up cosmic expansion. In dense regions full of galaxies, gravity fights against dark energy, slowing down the expansion in those areas. Inside voids, gravity loses that fight. Dark energy wins easily. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their edges outward, while the chains of galaxies around them act as walls. This creates a cycle that feeds itself. The more a void expands, the emptier it gets, which lets it expand even faster. Scientists proved this through careful watching. They measured how galaxies near void edges move compared to galaxies in denser regions. The void galaxies are rushing away from the center faster than cosmic expansion alone would explain. Something is pushing them outward. That something is the gravitational pull from all the matter outside the void. Think of a void like a valley surrounded by mountains. Gravity pulls downhill from the mountains toward the valley. But since we're talking about space rather than land, that pull makes galaxies fall outward, not inward. The effect is real and significant. Our own galaxy is moving away from the local void at 600,000 mph, driven by this gravitational imbalance. The inside of a void becomes a strange place for physics. Light travels through it, experiencing less gravitational influence than light passing through normal space. This affects what we see in subtle ways. When astronomers study the cosmic microwave background radiation, the faint glow from the Big Bang, they notice that light passing through voids looks slightly cooler. The reduced gravity in voids causes less gravitational redshift, showing up as cold spots in temperature maps of the early universe. These cold spots line up perfectly with where we see large voids today. This match isn't coincidence. It's physics. Understanding what makes voids empty helps explain why they matter so much to cosmology. They're not just boring blank spaces between interesting galaxy clusters. They're places where dark energy rules and where gravity takes a back seat. By studying how matter acts differently in voids versus dense regions, scientists can test basic theories about how the universe works. The KBC void around us might be unsettling because it makes us question whether our place in the universe is special, but it also gives us a rare chance. We're positioned in exactly the right spot to study the universe's most extreme low-density places. The structure that holds these voids is far stranger than anyone imagined. The universe isn't a smooth soup of evenly spread galaxies. Instead, it looks like Swiss cheese, where dense matter forms walls and threads surrounding huge hollow pockets. This foam-like shape is called the cosmic web, and it's the largest structure in nature. Galaxy clusters gather at the intersections where multiple threads meet, creating knots of intense matter density. These knots shine brightly with millions of galaxies packed relatively close together. Stretching between them run filaments, long chains of galaxy groups that can reach for hundreds of millions of light years. These filaments form walls, huge sheets where galaxies gather in higher than average numbers. Between the filaments and walls lie the voids, taking up most of the space while containing hardly any mass. This structure wasn't always obvious. For decades, astronomers photographed the sky and counted galaxies. But the true three-dimensional layout stayed hidden. Distance measurements were poor. Galaxies that looked next to each other might actually be separated by billions of light years, with one much farther away than the other. Only when scientists began measuring galaxy redshifts systematically in the 1970s and 80s did the cosmic web reveal itself. Redshift surveys let astronomers figure out how far away each galaxy was by measuring how much the expansion of space had stretched its light toward redder wavelengths. Suddenly, the pattern snapped into focus. The universe had structure on scales nobody expected. The first major void discovery came in 1978 when two independent teams found large, low-density regions. More surveys followed, each mapping deeper into space and showing an increasingly complex web. The Sloan Digital Sky Survey, which started in 2000, created amazing three-dimensional maps spanning billions of light years. These maps show the cosmic web in stunning detail. Filaments twist and branch like blood vessels. Voids appear as dark bubbles, sometimes 500 million light years across. The largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light years long. On the opposite end, supervoids like the Eridanus Void stretch 1.8 billion light years wide, with even fewer galaxies than the KBC Void. Together, these features paint a picture of a universe organized on scales far larger than anyone predicted. Galaxies aren't the basic building blocks. The web itself is the structure, with galaxies just marking where the matter happens to gather. Why does the universe organize this way? The answer goes back to the beginning. Right after the Big Bang, matter wasn't perfectly even. Quantum fluctuations during the universe's first tiny fraction of a second created small changes in density. Some regions were slightly denser than average, others slightly less dense. These differences were tiny, maybe 1 part in 100,000. But gravity makes even tiny advantages bigger. Denser regions pulled in more matter, making them denser still. Less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, this process snowballed. Small clumps merged into larger clumps, which merged into galaxy clusters, which lined up into filaments. Meanwhile, the low-density regions expanded into voids. The cosmic web is basically gravity doing its work over cosmic time, turning barely noticeable early ripples into the grandest structure in existence. Today, voids take up roughly 90% of the space. Filaments and clusters make up the remaining 10%, but contain most of the mass. This imbalance defines what the universe is like. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness dotted by occasional groupings of matter. The KBC void is just one bubble in this foam, but it happens to be our bubble, and that makes all the difference for what we see and how we understand the universe. The next part shows exactly where we sit inside this huge hollow. The Milky Way isn't at the center of the KBC void, but it's close enough to matter. Measurements put our galaxy somewhere between 200 and 400 million light years from the void's actual center. That might sound like a huge distance, and it is compared to anything humans know. But the void extends outward for 1 billion light years in every direction from its center, making our offset relatively small. We sit well within the low-density region, surrounded by the void's thin environment in all directions. This position isn't random. It has effects on every observation we make and every conclusion we reach about cosmology. If we were located outside the void entirely, in one of the dense filaments, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate, and the Hubble tension wouldn't exist. Our larger cosmic neighborhood adds another layer to this story. The Milky Way belongs to the local group, a collection of about 80 galaxies, including our giant neighbor Andromeda. The local group itself sits within the Laniakea supercluster, a massive structure holding roughly 100,000 galaxies spread across 520 million light-years. Laniakea is huge by any normal standard. Yet even this supercluster lives within the KBC void. Think about that for a moment. A structure containing 100,000 galaxies still counts as part of a low-density region. The void is so huge that it can swallow entire superclusters and still have room left over. Laniakea forms part of the sparse matter scattered through the void, one of the rare concentrations in an otherwise empty expanse. The local group is also influenced by another nearby void called the local void, which is different from but connected to the larger KBC void. The local void extends about 200 million light-years and sits next to our position. Our galaxy is rushing away from it at 600,000 mph, pushed by the gravitational pull from denser regions beyond. This motion is separate from the overall cosmic expansion. It's a peculiar velocity, meaning it comes from local gravitational effects rather than the stretching of space itself. These peculiar velocities make efforts to measure the true expansion rate harder because they add extra motion on top of the expansion signal. Astronomers must carefully account for these local effects. But inside a supervoid, those effects are stronger and harder to separate cleanly. The void's influence reaches even farther. When scientists measure the motion of galaxies out to distances of 250 million light-years, they find bulk flows that go beyond what standard cosmology predicts. Entire regions of space are moving faster than they should be, flowing in steady patterns driven by the void's gravitational imbalance. The KBC void creates a large-scale velocity field that affects everything within it. Galaxies aren't just sitting in an empty region, quietly expanding with the universe. They're actively responding to the gravitational landscape, speeding outward from the low density toward denser structures beyond the void's edge. This makes our local patch of the universe more active and unusual than the calm, even cosmos that standard models assume. Our position inside the void also affects what we can see. Light from distant galaxies travels through the void on its way to our telescopes. That light experiences less gravitational interaction than light traveling through denser regions. The reduced gravity creates subtle effects on the light's wavelength and energy. Additionally, the void itself influences the spread of matter we observe. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as a gathering of galaxy clusters and filaments at a specific distance range. Beyond the shell, the universe returns to more typical density. This creates an observational bias. We're not sampling a random location in the universe. We're sampling from inside one of its most extreme features. Living in the void means living with systematic uncertainty about how typical our measurements really are. Every measurement you've ever heard about the universe's expansion rate might be wrong. Not because scientists made mistakes, but because we're measuring from inside a cosmic hole that warps the signal. The problem shows itself when astronomers use different methods to calculate the Hubble constant, the number that tells us how fast space expands. One method looks at the cosmic microwave background, ancient light from when the universe was just 380,000 years old. This light holds information about the early universe's density and expansion rate. Scientists feed this data into models and calculate what the expansion rate should be today. The answer comes out to about 67 kilometers per second per megaparsec. That means for every megaparsec of distance, roughly 3.3 million light-years, space expands at 67 kilometers per second. The second method looks at nearby objects with known brightness, specifically type Ia supernovae and Cepheid variable stars. These objects serve as cosmic measuring sticks because astronomers understand exactly how bright they should be. By comparing their actual brightness to their apparent brightness as seen from Earth, scientists calculate their distance. Combining distance measurements with redshift measurements gives the expansion rate directly. This local method consistently gives a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are incredibly precise, with very small error margins. Both should give the same answer if cosmology is correct. They don't. This gap is the Hubble tension, and it has reached 5 sigma statistical significance, meaning there's less than a 1 in a million chance. It's just random variation. The KBC void explains why these numbers disagree. When we measure the expansion rate using nearby supernovae, we're measuring within the void. The void's low density means less gravity pulling back on the expansion. Matter from the denser regions outside the void gravitationally attracts galaxies within it, adding extra outward speed. Galaxies appear to move away faster than they would in a typical region. This inflates the local Hubble constant measurement. We're not measuring the universe's true expansion rate. We're measuring the expansion rate plus the void's peculiar velocity field. The effect is large enough to account for most or all of the observed tension. When scientists model how a void of the KBC's size and depth would affect local measurements, they find it could boost the apparent expansion rate by exactly the amount needed to match what we see. But here's where it gets uncomfortable. If the void explains our local measurements, then those measurements might be systematically biased by our location. Some scientists resist this conclusion because it violates the cosmological principle, the assumption that Earth doesn't occupy a special location. The principle states that the universe should look roughly the same from any viewpoint once you average over large enough scales. Finding ourselves inside a supervoid that significantly affects our measurements seems to contradict that idea. It suggests we're in an unusual location, which makes physicists uncomfortable. Science has progressively removed humanity from special cosmic positions. Earth isn't the center of the solar system. The solar system isn't the center of the galaxy. The galaxy isn't the center of anything. And now we're supposed to believe we just happen to live inside one of the largest voids ever observed. The statistical improbability bothers many researchers, yet the evidence keeps mounting. The void exists. Our measurements are different. The void's effects match what we see. Whether we like it or not, the universe might actually be lying to us about its expansion rate. Or more precisely, our location is causing us to misunderstand what we measure. The crisis this creates in cosmology goes deeper than most people realize. The Hubble tension isn't just an annoying disagreement between two measurements. It represents a basic challenge to our understanding of cosmic evolution. Cosmology rests on a framework called lambda cold dark matter, or the standard model of cosmology. This model has been incredibly successful at explaining observations from multiple sources. It accounts for the cosmic microwave background temperature fluctuations, the abundance of light elements like hydrogen and helium, the formation of galaxies, and the large-scale structure of the universe. For decades, it's been the accepted model, because it works so well in so many contexts. But the Hubble tension suggests something is missing or wrong in this framework. When a model's predictions disagree with observations at the 5 sigma level, scientists must take that seriously. The tension matters because the expansion rate determines everything else about cosmic history. If the universe expands faster, it reaches its current size in less time, making the universe younger. Current calculations based on the cosmic microwave background put the universe's age at 13.8 billion years. But if the higher local measurement is correct globally, the universe might be only 12.7 billion years old. That creates immediate problems. We observe stars in globular clusters that appear to be 13 billion years old based on stellar evolution models. These stars would be older than the universe itself, which is impossible. Either our age measurements for stars are wrong, our understanding of stellar physics is wrong, or the higher Hubble constant doesn't apply to the early universe. None of these options are comfortable. The tension also affects our understanding of dark energy, the mysterious force accelerating cosmic expansion. Dark energy makes up about 68% of the universe's total energy, according to standard models. But its properties depend sensitively on the expansion rate. If the expansion rate is higher than we thought, dark energy's behavior might be different than current models assume. Some researchers have proposed that dark energy evolves over time rather than being constant, which would be revolutionary. Others suggest we need to add new physics to the early universe, perhaps an extra burst of accelerated expansion shortly after the Big Bang. Every proposed solution introduces new complications and requires evidence beyond just fixing the Hubble tension. Dozens of alternative explanations have been put forward. Some scientists propose that the measurements themselves contain subtle systematic errors that have been overlooked. Perhaps dust between galaxies dims supernovae more than accounted for, making them appear farther away and inflating the expansion rate. Or maybe Cepheid variable stars behave differently in different environments, biasing their use as distance indicators. These explanations keep getting tested and ruled out as measurement techniques improve. The measurements are solid. Other researchers suggest modifications to general relativity, Einstein's theory of gravity. Maybe gravity works slightly differently on cosmological scales than we think, which would change predictions for expansion. This route leads into controversial territory because general relativity has passed every other test thrown at it. The void hypothesis offers a cleaner solution that requires less modification to fundamental physics. It simply states that we're in an unusual location, and our local measurements reflect that rather than reflecting universal properties. This explanation bothers people philosophically, but requires fewer assumptions than inventing new particles or changing gravity. Recent work has strengthened the void hypothesis by showing it naturally predicts other observations. For example, the outflow velocity from the void should affect not just the expansion rate, but also the motion of galaxy clusters in our area. Measurements of these bulk flows match the void predictions. The hypothesis is making testable predictions that are being confirmed. Nevertheless, debate continues. Not all cosmologists accept the void explanation. Some argue that even a void as large as the KBC can't produce a big enough effect to fully explain the tension. Others point out that supervoids this large should be rare, and finding ourselves in one just when we develop the precision to measure the Hubble constant seems suspicious. Maybe we're reading the data wrong somehow. The controversy remains unsolved, which is why the Hubble tension continues to be called a crisis. It's not just a number that's off. It's a signal that our understanding of the cosmos might be incomplete. Understanding how gravity creates this mess requires looking at how forces work in empty space. Gravity inside a void does something counterintuitive. It pushes outward instead of pulling inward. This isn't because gravity itself reverses. The force of gravity always attracts mass toward mass, but the geometry matters. Imagine standing in a shallow valley surrounded by mountains. Gravity pulls you toward the mountains, which means pulling you away from the valley's center. Inside a cosmic void, galaxies experience the same effect. All the matter lies outside the void in the surrounding filaments and clusters. That exterior matter gravitationally attracts the interior material, pulling galaxies outward from the void center toward the denser regions beyond. The result is an outflow, a systematic pattern of galaxies accelerating away from the low density region. This outflow is measurable and significant. Astronomers can track galaxy velocities using redshift measurements combined with distance estimates. When they map velocities around known voids, the pattern is clear. Galaxies near void centers are moving faster outward than cosmic expansion alone predicts. The effect is strongest near the void center and weakens toward the edges where matter density increases. For the KBC void specifically, the outflow adds hundreds of kilometers per second to galaxy velocities within the void. Our own galaxy participates in this pattern. The Milky Way is moving at 600,000 mph away from the nearby local void, driven by the gravitational imbalance. This motion combines with other local effects, like the gravitational pull from the Virgo cluster, to create our galaxy's overall peculiar velocity. The outflow has implications for cosmic expansion measurements. When we observe distant galaxies and measure their redshift, we're seeing a combination of two effects: the expansion of space itself and the peculiar motion of galaxies due to gravity. Normally, scientists can separate these parts because peculiar velocities average out when you look at large enough volumes. For every galaxy moving toward you due to local gravity, another galaxy is moving away, and the average is zero. But inside a void, the peculiar velocities don't average out. They all point in the same direction, outward. This creates a systematic bias that inflates the apparent expansion rate when measured from within the void. The problem compounds at different distance scales. Close to the void center, the outflow is rapid. Farther from the center, but still within the void, the outflow is slower. Beyond the void's edge, the peculiar velocities might even reverse as matter falls back toward the denser filaments. This creates a complicated velocity profile that varies with distance. When astronomers measure the Hubble constant using supernovae at different distances, they're sampling this varying velocity field. If most of their supernovae lie within the void, which they do because we deliberately avoid using extremely distant supernovae due to other complications, the measurement gets boosted by the outflow. The farther out you measure, the less the void affects the result. This predicts that the Hubble constant should appear to decrease with distance, and recent observations confirm exactly that trend. Modeling these effects requires careful calculation. Scientists must estimate the void's size, depth, and density profile, then calculate the gravitational potential it creates. That potential determines how fast material flows outward at each radius. The calculations show that a void roughly 1 billion light-years in radius, with a 20% density deficit, can easily produce the observed velocity oddities. The match between predictions and observations is good enough that many researchers find the void explanation compelling. However, the standard cosmological model struggles to explain how such a large void formed in the first place. Computer simulations based on lambda cold dark matter rarely produce voids this extreme. When they do, it requires very specific starting conditions that are statistically unlikely. This raises a troubling possibility. Maybe our cosmological model is missing something. If voids larger and deeper than expected keep showing up in observations, perhaps structure formation works differently than standard theory predicts. Some scientists propose modified gravity theories where gravity is stronger on large scales, which would enhance structure formation and make big voids more common. Others suggest that the universe is simply more lumpy than assumed, which would also make large voids less surprising. Either way, the backwards gravity in voids is telling us something important about cosmic evolution. Our motion through this gravitational landscape is faster than anyone expected. The Milky Way isn't sitting still in space. It's falling through the cosmos at 600,000 mph, roughly 850 times the speed of sound. This velocity isn't from the expansion of space, but from local gravitational effects. Specifically, our galaxy is being pulled away from the local void and toward the denser structures beyond it. The local void is different from but connected to the larger KBC void, and it exerts a strong influence on our motion. The void itself isn't pushing us. Rather, the deficit of matter in the void means there's less gravity pulling us toward it compared to the gravity pulling us in other directions. The denser regions win the tug of war, accelerating our galaxy away from the low density. This speed is difficult to comprehend. 600,000 mph means the Milky Way travels about 167 miles every second. In a single year, our galaxy moves about 5.2 billion miles through space relative to the void. But even at this breakneck pace, the void is so vast that our motion barely makes a dent. It would take hundreds of millions of years to cross from one side of the void to the other, even at this speed. Meanwhile, the void continues expanding due to cosmic expansion and dark energy, growing faster than we can escape it. We're inside the void now, and will remain inside it for the foreseeable cosmic future. The local sheet adds another part to our motion. The local sheet is a flattened structure of galaxies that includes the Milky Way, Andromeda, and other nearby galaxies. This sheet forms one wall of the local void. The entire sheet is rushing away from the void center at about 260 kilometers per second, which is roughly 580,000 mph. Our galaxy participates in this bulk motion along with its neighbors. The sheet isn't static. It's actively being drained from the void region, flowing outward like water draining from a depression. This motion has been going on for billions of years and will continue for billions more. But there's more to our velocity than just escaping the void. The Milky Way is also falling toward the Virgo cluster, a rich gathering of galaxies about 60 million light-years away. The Virgo cluster contains over 2,000 galaxies and has enough mass to gravitationally attract everything in the surrounding region, including us. This adds another part to our peculiar velocity, roughly 250 kilometers per second, directed toward Virgo. Meanwhile, the Milky Way and Andromeda are falling toward each other and will collide in about 4 billion years. That motion adds yet another velocity component. When you add up all these gravitational influences, the Milky Way's total peculiar velocity relative to the cosmic microwave background rest frame is about 627 kilometers per second. That's the velocity astronomers measure when they look at the dipole pattern in the cosmic microwave background temperature. These motions matter because they complicate cosmological measurements. When we observe distant galaxies and measure their redshift, we need to correct for our own motion through space. Otherwise, galaxies in the direction we're moving appear blue-shifted, and galaxies in the opposite direction appear red-shifted, creating a false pattern that mimics cosmic structure. Astronomers have known about these corrections for decades and routinely apply them. But inside a void, the corrections become more complicated because the void itself creates large-scale bulk flows that extend over hundreds of millions of light-years. Disentangling the void effect from the true cosmic expansion requires careful modeling of the local velocity field. Our high speed through space is itself evidence for the void. If we lived in a typical region with average density, our peculiar velocity would be much smaller, maybe 100 or 200 kilometers per second at most. The fact that we're moving so fast indicates strong gravitational gradients in our area, exactly what you'd expect from being near a large, low-density region. The velocity is consistent with the void hypothesis and would be difficult to explain without it. This makes our motion a key piece of evidence in the debate over whether the KBC void exists and whether it affects our measurements. The universe may be lying to us about its expansion rate, but it can't hide the fact that we're racing through it at incredible speed. This motion connects to a deeper principle that the void fundamentally violates. The cosmological principle is one of the foundational assumptions of modern physics, and the KBC void threatens to shatter it. The principle states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. No location is special or different from any other when you average over large regions. Isotropic means the same in all directions. The universe looks the same no matter which way you look. These assumptions simplify the mathematics of cosmology enormously. They let scientists model the entire universe using relatively straightforward equations. Without the cosmological principle, the equations become vastly more complicated, and predictions become much harder to make. The principle has been remarkably successful, accurately describing many observations. But the KBC void represents a major violation of homogeneity. If the void is 2 billion light-years across with a 20% density deficit, that's a huge irregularity. Even on cosmic scales, the void isn't small compared to the observable universe. It represents a significant fraction of the volume within several billion light-years of Earth. More troubling, we happen to live near the center of this abnormal structure, which seems to contradict the idea that our location is unremarkable. Throughout history, science has progressively removed Earth from any special position. Copernicus showed Earth wasn't the center of the solar system. Later observations showed the solar system wasn't the center of the galaxy, and the galaxy wasn't the center of anything. The cosmological principle is the ultimate expression of this trend. Not only is Earth not at the center, but there is no center because every location is equivalent. The void challenges that worldview. If we live inside an abnormally large, low-density region, our location is unusual by definition. Voids are common in the universe, but most are smaller than the KBC void. Supervoids this large are rare. Finding ourselves in one raises questions about whether the cosmological principle truly holds, or whether it's only approximately true on scales much larger than previously thought. Some scientists calculate that in a universe governed by standard cosmology, a void as large and deep as the KBC void should be exceedingly rare, perhaps a 10 sigma statistical deviation. In a typical random version of the universe's structure, you might not find one anywhere in the observable cosmos. Yet, we're in one. This suggests either we're incredibly lucky, or the standard model is wrong about how structure forms. Defenders of the cosmological principle argue that the void doesn't actually violate the principle because homogeneity only applies at scales of several hundred megaparsecs or larger. The void is about 600 megaparsecs across, which is right at the edge of where homogeneity is supposed to kick in. Maybe the universe is less smooth at those scales than we assumed. Alternatively, maybe the void isn't as extreme as measurements suggest. Different observational techniques give somewhat different density contrasts for the void. If the true deficit is closer to 10 or 15% rather than 20%, the statistical rarity becomes less severe. These counterarguments preserve the cosmological principle, but require accepting that our measurements are less precise than we thought. Another defense is that we shouldn't be surprised to find ourselves in an unusual location, because observers can only exist in certain types of environments. This is a weak anthropic argument. Perhaps intelligent life requires galaxies to form, and galaxies form preferentially in moderately dense regions rather than in the densest clusters or the emptiest voids. If most observers live in mildly low density regions, then finding ourselves in a slight void isn't surprising. But this argument only works if the KBC void isn't as extreme as it appears. A 20% deficit is more than mild. It pushes the boundary of what the anthropic principle can explain away. The debate over the cosmological principle isn't settled. Some researchers believe the void is real and significant, requiring either modifications to cosmology or acceptance that Earth occupies a genuinely unusual position. Others believe the void is an observational artifact, or not as extreme as initially reported. Still others propose that the principle holds on even larger scales and that the apparent violation is temporary. Future observations should help resolve this. Surveys that map the universe to greater distances and depths will reveal whether large voids are as rare as standard models predict, or whether they're more common than expected. If big voids turn out to be frequent, the cosmological principle survives, but the standard model needs revision. If they're truly rare, we need to explain why we happen to live in one. The origin of these voids reaches back to the universe's first moments. The voids we observe today began as infinitesimal quantum ripples in the first moments after the Big Bang. During a period called inflation, the universe expanded exponentially for a tiny fraction of a second, perhaps 10 to the negative 35 seconds. During this expansion, quantum fluctuations were stretched from subatomic scales to cosmic scales. These fluctuations created slight variations in the density of matter and energy. In some regions, density was a tiny bit higher than average. In others, it was a tiny bit lower. The variations were incredibly small, about 1 part in 100,000, but they were enough to set the stage for everything that followed. After inflation ended, the universe continued expanding, but at a much slower rate. Matter began to clump together under gravity, but the gravitational pulling only amplified the initial density differences. Regions that started slightly denser attracted more matter from their surroundings, making them denser still. This created a positive feedback loop. The denser a region became, the more strongly it pulled matter toward itself. Over millions of years, these overdense regions collapsed into the first stars, then galaxies, then clusters of galaxies. Meanwhile, regions that started slightly less dense lost matter to their denser neighbors. As matter drained away toward the collapsing overdense regions, the low-density regions became even emptier. These low-density regions evolved into voids. The process is called gravitational instability, and it turned barely perceptible initial ripples into the dramatic large-scale structure we observe today. The cosmic microwave background radiation provides a snapshot of these density variations when the universe was only 380,000 years old. At that time, the variations were still tiny, visible only as slight temperature differences of about 100 millionths of a degree. But those temperature differences correspond directly to density differences. Warmer spots had slightly higher density. Cooler spots had slightly lower density. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft have mapped these temperature variations in exquisite detail across the entire sky. Maps show a modeled pattern of hot and cold spots at various angular scales. This pattern encodes the seeds of structure formation. Scientists can take this pattern and run it forward in computer simulations to predict how structure should look billions of years later. Those simulations reliably produce a cosmic web of filaments, clusters, and voids that closely resembles what we observe. The match between predictions and observations is one of the great successes of modern cosmology. It confirms that our understanding of how gravity shapes structure over cosmic time is largely correct. However, the simulations rarely produce voids as large or as deep as the KBC void. This is where tension arises. The initial quantum fluctuations were random, so every region had some chance of ending up as a void or a filament. But probability distributions matter. Small voids should be common. Medium voids should be less common. Extremely large voids should be very rare. The KBC void appears to fall into the extremely rare category, which raises questions about whether our simulations are missing something. One possibility is that the initial quantum fluctuations weren't completely random, but had subtle patterns that enhanced the formation of large voids. This could happen if inflation didn't smooth out structure as uniformly as standard models assume. Another possibility is that gravity works slightly differently on large scales than general relativity predicts, which would change how voids form and evolve. A third option is that the universe simply has more variance in structure than cosmologists expected, making large voids less surprising. Each of these explanations requires further evidence. Observations of more distant voids in other parts of the universe would help determine how rare the KBC void truly is. If similar voids turn up frequently, it suggests the standard model underestimates structure variance. If they remain exceedingly rare, it strengthens the case for modified physics or unusual initial conditions. The quantum origin of voids is both elegant and unsettling. It means that the cosmic desert we inhabit traces back to subatomic processes that occurred before atoms even existed. Randomness at the smallest scales propagated upward to create structure at the largest scales. The universe's organization isn't designed or predetermined. It's the consequence of random quantum fluctuations amplified by gravity over billions of years. This realization is one of the profound insights of modern cosmology, but it also means that our location within this structure is the result of chance. There's no reason we had to end up in a void rather than in a filament. We're here because the initial conditions in our region happened to be slightly low density. That accident of quantum chance 14 billion years ago determines what we observe when we look out at the cosmos today. The scale of these empty regions dwarfs human imagination. When you picture the universe, you probably imagine a sky full of stars and galaxies. But the reality is the opposite. The universe is overwhelmingly empty. Voids occupy roughly 90% of the total volume of space. Galaxies and galaxy clusters crowd into the remaining 10%, packed into filaments and walls that surround the voids. This isn't just empty space in the sense of vacuum between stars. It's empty in the sense that entire regions hundreds of millions of light years across contain almost no galaxies at all. If you could travel through a void, you would fly for tens of millions of years at the speed of light without encountering a single galaxy. The isolation would be nearly absolute. This distribution creates a lopsided universe. Most of the matter concentrates in a small fraction of the volume. The filaments are crowded with galaxies that interact, merge, and evolve rapidly. Star formation is vigorous. Black holes grow. Galaxies collide and trigger bursts of star creation. Meanwhile, the voids are quiet. A few lonely dwarf galaxies drift through the darkness, separated by vast distances. These void galaxies evolve slowly because they rarely interact with neighbors. They tend to be smaller, fainter, and less evolved than galaxies in dense regions. Star formation is sluggish. Many void galaxies contain large amounts of neutral hydrogen gas that hasn't yet condensed into stars. They're galactic backwaters, isolated from the busy highways of the cosmic web. The extreme emptiness of voids raises questions about how empty space can really be. Even in voids, dark matter is present. Dark matter makes up about 85% of all matter in the universe, but doesn't interact with light, making it invisible to telescopes. It's detectable only through its gravitational effect. In voids, dark matter is much less concentrated than in filaments, but it still exists at about 15% of the cosmic average density. That might sound like a lot, but spread over such huge volumes, the amount of dark matter per cubic light year is incredibly tiny. Additionally, voids contain dark energy, the mysterious component driving cosmic acceleration. Dark energy appears to be uniform throughout space, so voids have just as much dark energy per volume as dense regions. In fact, because dark energy doesn't clump like matter, it becomes the dominant component in voids where matter is scarce. The interplay between dark matter and dark energy determines void evolution. In the early universe, matter dominated even in low-density regions, and gravity still mattered. As the universe expanded and dark energy became more important, voids began accelerating their expansion. This acceleration makes voids grow faster over time, eating into the surrounding filaments. Eventually, if dark energy continues to dominate, voids will consume more and more of the universe. Filaments will thin out. Galaxy clusters will become isolated islands in an expanding ocean of emptiness. Billions of years in the future, the universe will be even emptier than it is now, with voids occupying an even larger fraction of the total volume. This future evolution is inevitable given what we understand about dark energy. The universe's destiny is to become increasingly hollow. Understanding the void fraction of the universe is important for interpreting observations. When we measure the average properties of the universe, such as the overall matter density or the expansion rate, we're averaging over both voids and filaments. If we don't account for the fact that most space is void, we might misunderstand what those averages mean. For instance, measurements of the cosmic microwave background give the average matter density of the universe, which is about 30% of the critical density needed to stop cosmic expansion. But that average includes both the dense filaments and the sparse voids. The local density varies dramatically depending on where you are. In a filament, the density might be 3 times the average. In a void, it might be 15% of the average. These variations matter when trying to understand local observations. The 90% void fraction also affects searches for rare phenomena. For example, astronomers searching for distant supernovae or gamma-ray bursts are most likely to find them in the dense filaments where star formation is active. Finding these events in voids is much rarer because voids contain fewer galaxies and less star formation. This creates an observational selection effect. Most of the interesting astronomical events happen in the busy 10% of the universe, not the quiet 90%. We study the universe from within the active regions and mostly ignore the empty ones. But the voids are just as much a part of cosmic reality as the filaments. Understanding them is essential for understanding the universe as a whole. One void stands out as particularly impossible under current physics. The KBC void defies probability in a way that makes cosmologists deeply uncomfortable. Standard cosmology predicts that structures form through gravitational collapse of initial density fluctuations. The larger and deeper a structure, the rarer it should be. Small voids, a few tens of millions of light years across, are common because they arise from common small fluctuations. Large voids, hundreds of millions of light years across, are less common because they require larger, rarer fluctuations. The KBC void is 2 billion light years across and 20% low density. Computer simulations of structure formation using the lambda cold dark matter model rarely produce anything this extreme. When researchers run thousands of simulated universes and look for voids as large and deep as the KBC void, they find very few matches. The statistical likelihood of such a void existing is extremely low. Some studies have estimated the improbability. One analysis calculated that a void of the KBC's size and depth represents a 10 sigma deviation from the expected density. In statistics, a 5 sigma result means there's less than a 1 in a million chance of it being random. A 10 sigma result is incomprehensibly unlikely. You would need to observe trillions of universe-sized volumes to expect to find even one such void. Yet here we are, living in one. This isn't a small statistical oddity. It's a massive red flag, suggesting something is wrong with either the observations or the model. If the observations are correct, which multiple independent studies suggest they are, then the model must be missing something. One possibility is that the initial density fluctuations after the Big Bang weren't as smooth as standard inflation models predict. If inflation produced more power on large scales than expected, large voids would form more easily. This would require modifying our understanding of inflation, which is already a speculative part of cosmology with limited direct evidence. Another possibility is that structure formation proceeded faster or differently than standard models predict. If gravity was effectively stronger in the past, or if dark matter behaves differently than assumed, structure would form more vigorously, creating larger voids and richer clusters. Some researchers propose modified gravity theories, where the strength of gravity varies with scale or environment. These theories can enhance structure formation and make large voids more likely. A third option is that the KBC void isn't as extreme as measurements suggest. Perhaps observational biases or systematic errors in galaxy surveys have made the void appear deeper and larger than it really is. Different groups using different data sets have measured the void's properties and found somewhat different results. Some studies find a 20% density deficit. Others find closer to 10 or 15%. If the true deficit is on the lower end, the statistical rarity becomes less severe, though it remains a challenge for standard models. Confirming the void's exact properties requires more data, particularly deeper galaxy surveys, that can map the void's extent and density profile with higher precision. Future missions like the Euclid Space Telescope and the Vera Rubin Observatory will provide much better data. The existence of the KBC void has become ammunition in debates about whether standard cosmology needs revision. Skeptics of the lambda cold dark matter model point to the void as evidence that something fundamental is wrong. Defenders argue that rare events do happen, and we shouldn't be shocked to observe one eventually. They compare it to winning the lottery. Someone wins even though the odds for any individual ticket are astronomically small. But the lottery analogy breaks down when you realize we've only observed one draw, our own local universe, and we happen to hit the jackpot. If we could observe thousands of independent universe volumes and found KBC scale voids in only one, that would be consistent with rarity. But we can't do that. We're stuck with just our local observations, and those observations keep challenging our models. The void's existence forces cosmologists to grapple with uncomfortable questions. Is our understanding of structure formation incomplete? Are we overconfident in our statistical models? Or are we simply living in an extremely unlikely location? None of these answers are satisfying, which is why the debate continues. What makes this especially frustrating is that the void hypothesis solves the Hubble tension so cleanly. If the void is real and affects our measurements, then the tension disappears. The two different expansion rate measurements are both correct. They're just measuring different things. The local expansion rate within the void versus the global expansion rate of the entire universe. But accepting this solution means accepting that Earth occupies a highly unusual location, which violates cherished principles about cosmic democracy. Scientists don't like coincidences. Finding ourselves in a statistically improbable location just when we're trying to measure cosmic parameters seems too convenient. Yet the alternative is to reject the void explanation and search for other solutions to the Hubble tension, none of which have proven as compelling. The KBC void represents a crisis at multiple levels. It challenges our statistical expectations, our cosmological models, and our philosophical assumptions about where we are in the universe. Resolving this crisis will require either better observations that clarify the void's properties or theoretical breakthroughs that explain how such structures form more easily than current models allow. Meanwhile, astronomers continue mapping the universe, searching for similar voids at greater distances. If KBC scale voids turn out to be more common than predicted, that's a problem for standard models, but potentially good news for cosmology. It would mean we're not in such a special location after all. Large voids are just more common than we thought. But if the KBC void remains unique in its size and depth, the mystery deepens. Future surveys will map billions of galaxies across cosmic time, creating three-dimensional maps of unprecedented detail. These maps will reveal whether our local void is truly unusual or whether we've simply been looking at too small a sample. The answer will determine whether cosmology needs a minor adjustment or a major overhaul. The void's threat to everything we think we know goes beyond just cosmology. It touches fundamental questions about observation, measurement, and how we understand reality. If our location systematically biases every observation we make, then how can we claim to understand the universe as a whole? Every measurement we've ever made was taken from this one spot inside this one void. Our telescopes all point outward from the same gravitational environment. Our understanding of cosmic expansion is based on light that traveled through the same underdense region to reach us. Our maps of galaxy distribution all center on the same unusual location. This creates a profound epistemological problem. How do we know what's typical and what's local bias? Scientists try to account for local effects by studying how galaxies move, measuring the cosmic microwave background from different directions, and comparing observations at different distances. But if the void is large enough, it affects everything within it, making it hard to find a clean reference point. We need to observe from outside the void to truly understand what's typical, but we can't do that. This limitation isn't unique to the void problem. All astronomy suffers from the fact that we can only observe from one location. We can't move to another galaxy and repeat our measurements to see if we get the same results. We're stuck with a sample size of one observing point Earth. The void makes this limitation acute because it introduces a systematic bias that's large enough to matter, but hard to correct for. Every correction we apply depends on models of how the void affects observations, and those models depend on assumptions about cosmology that might themselves be wrong. It's a circular problem. We need to know the void's properties to correct our measurements, but we need accurate measurements to determine the void's properties. Breaking this circle requires independent lines of evidence that don't depend on the same assumptions. Some of those lines of evidence come from the cosmic microwave background, because this radiation comes from the early universe before voids formed. It provides a snapshot of conditions unaffected by local structure. The cold spots in the microwave background that correspond to void locations offer one way to study voids independently of galaxy surveys. Another approach is to look at how light from distant quasars gets absorbed by gas clouds as it travels through space. The pattern of absorption tells us about the distribution of matter along the line of sight. By studying many quasars in different directions, astronomers can map the three-dimensional density field without relying on galaxy counts. These absorption line surveys confirm the existence of voids and generally agree with galaxy-based maps. A third method involves gravitational lensing, where the gravity of matter bends light from more distant objects. By measuring how much lensing occurs in different directions, scientists can infer the density of matter, including dark matter, along the line of sight. Voids produce less lensing than dense regions. Lensing surveys provide yet another independent check on void properties. All these methods generally confirm that the KBC void exists and has properties consistent with the original discovery. The void isn't an artifact of one particular measurement technique. It shows up in multiple independent data sets using different physical principles. This strengthens the case that the void is real, but it also deepens the puzzle of why we're in it. The more we confirm the void's existence and properties, the more we have to grapple with its statistical improbability and its effects on our observations. The void won't go away just because it's inconvenient for our theories. This confronts cosmology with a choice. Either accept that we're in an unusual location and adjust our interpretation of observations accordingly, or search for alternative explanations that preserve the assumption of a typical location. Most scientists are pursuing both paths simultaneously, keeping an open mind about which will ultimately prove correct. The debate illustrates a healthy aspect of science, the willingness to question foundational assumptions when observations don't match predictions. The cosmological principle has been enormously useful, but it's an assumption, not a law of nature. If reality violates it, science must adapt. What happens next could redefine our place in the cosmos. The next decade will be crucial for resolving the mysteries surrounding the KBC void. Several major astronomical projects are underway or planned that will dramatically improve our understanding of cosmic structure. The Vera Rubin Observatory in Chile will begin operating soon, conducting the legacy survey of space and time. This survey will photograph the entire visible sky every few nights for 10 years, creating an unprecedented time-lapse movie of the universe. It will detect billions of galaxies and measure their positions and distances with high precision. This data will allow scientists to map the cosmic web in far greater detail, including the structure and extent of the KBC void. The Euclid Space Telescope, launched by the European Space Agency, is designed specifically to study dark energy and dark matter by mapping the large-scale structure of the universe. Over 6 years, it will observe billions of galaxies across 10 billion years of cosmic history. The resulting three-dimensional map will reveal how structure has evolved over time and whether voids as large as the KBC void are rare or more common than expected. NASA's Nancy Grace Roman Space Telescope, planned for launch in the coming years, will conduct similar surveys with complementary capabilities. Between these 3 missions, astronomers will have an extraordinary data set for studying cosmic structure. The surveys will extend far beyond the KBC void, mapping structure across billions of light years. If other KBC scale voids exist, these surveys will find them. If such voids turn out to be rare, matching the predictions of standard cosmology, then we'll have to accept that we're in an unusual location. If they're more common, it will require revising our models of structure formation. Either outcome will teach us something fundamental about how the universe works. Beyond mapping voids, these surveys will help resolve the Hubble tension by providing better measurements of cosmic expansion at different distances and epochs. By carefully tracking how the expansion rate varies with distance, astronomers can determine whether the higher local rate is truly due to the void or whether something else is going on. If the expansion rate smoothly decreases with distance as you move away from the void center, that would strongly support the void hypothesis. If the rate stays constant or varies randomly, it would suggest the void isn't the answer, and physicists will need to look elsewhere for an explanation. Theoretical work is also advancing. Cosmologists are developing more sophisticated simulations that include effects often neglected in standard models. For example, most simulations treat dark matter as perfectly cold, meaning its particles move slowly. But if dark matter has even slightly higher velocities, warm dark matter, it would affect how small-scale structures form. Some researchers are exploring whether warm dark matter or other variations could make large voids more common. Others are investigating whether feedback processes from star formation and black hole activity might affect structure on the largest scales. These feedback processes are known to be important in galaxies and clusters, but their effects on void formation are less well studied. Modified gravity theories are also getting renewed attention. If gravity works differently on scales of hundreds of millions of light years than it does in the solar system, it could change predictions for structure formation. Some modified gravity theories predict enhanced structure with richer clusters and deeper voids. Testing these theories requires precise measurements of how matter moves in different environments, which future surveys will provide. Whatever the outcome, the next decade will likely see significant progress on the void mystery. The question of whether we live in an unusual location will move from speculation to testable prediction. Data from multiple independent surveys will either confirm or refute the void's properties and its effects on our measurements. This progression represents science at its best, identifying a puzzle, gathering better data, testing competing hypotheses, and ultimately converging on the explanation best supported by evidence. The process takes time and requires patience, but it's how we make genuine progress in understanding nature. For those of us watching from Earth, the journey is fascinating. We're living through a period where cosmology is confronting its limits and potentially undergoing a significant shift. Whether the resolution involves accepting our unusual location, modifying fundamental theories, or discovering something entirely unexpected, the outcome will reshape our understanding of the cosmos. The KBC Void story isn't finished. It's still being written by astronomers making observations and theorists developing models. The next chapters will be written over the coming years as data from new surveys arrives and theories are tested against reality. We began by learning that we're falling through a 2 billion light-year hole in space. We've explored what that means for physics, cosmology, and our understanding of where we are. The void challenges us to question assumptions, refine measurements, and stay humble about what we think we know. In the end, the void might be lying to us about the universe's expansion rate, or it might be revealing a truth we weren't ready to accept. That Earth's location is far stranger than we ever imagined. If you want to explore more mysteries like this, make sure you're subscribed to Mr. Sleepy Science. There are countless wonders in the universe still waiting to be uncovered, and we'll be here to guide you through them, one cosmic mystery at a time. Until next time, sleep well under the stars, knowing you're falling through the largest hole in the universe.